All right, guys. So this video, or it's probably going to be a couple videos here, is going to go through Unit One. So remember, Unit One is probably one of our longest units because it covers a lot of stuff, but it's all connected. So Coulomb's law is a big part of Unit One. It's a big part of everything, but you, Unit One starts off with just your basic chemistry nomenclature. So you got to go back and review all that. This video, we're not going to spend time, going over how to name an ionic compound or a covalent compound, what the Roman numeral means, that kind of thing. That's all stuff that you needed to learn back in Chemistry 1. So you can go back and watch those videos and review that stuff. There's also, remember, organic is not a big part of it. So, like, organic nomenclature and that kind of thing is not going to be a part of the AP exam. They use organic compounds to ask you questions about molecular structure, so like shapes around specific atoms within the structure of the compound, hybridization around an atom in one of the compounds, bond angles, and then intermolecular forces, like why does this organic compound have a higher boiling point than that, right? And it comes down to, oh, well, this one has an alcohol group, which means it can hydrogen bond, and this one is just a hydrocarbon, so it just has London dispersion forces. So things like that. And so you don't have to know what an alcohol group is, but you have to know that when you have O bonded to H within your organic structure, now your molecule's polar, and because you have that fond bond, H bonded to O, then one of the IMFs that molecule has, or that compound has, is hydrogen bonding. So again, the organic part of it's not that big of a deal, but it's about IMFs, about molecular shape, about polarity, about structure. They'll use organic compounds to ask you questions about those topics. And then it's atomic structure, so protons, neutrons, electrons, structure of atoms, structure of ions, and periodic trends, atomic radius, ionic radius, electronegativity, ionization energy, first ionization energy, then first, second, third, fourth, fifth, sixth, etc. ionization energies, which is all about how attracted are the electrons to the nucleus. You get this fight, this balancing act between electrons attracting to the nucleus, because that's where the positive charge is, but then they're repelling each other. So like core electrons shielding valence electrons from the nucleus. So you have this repulsion, Coulombic repulsion, but you have the Coulombic attraction, and that net balance is what kind of creates how big the atom or ion is going to be versus how small the electron cloud is going to be, or the radius of the atom or the ion is going to be. So those are the kind of important things to review in Unit 1. And then also we talked about ionic structure, metallic structure, structure of alloys, knowing what compounds or elements are considered network covalent structures, and they have really high melting points, like carbon diamond or carbon graphite or silicon or silicon dioxide. Those are network covalent structures, so they're going to be really strong, meaning having high melting points and that kind of thing. So a lot of stuff is covered in Unit 1. It's about 25% of the AP exam, so you want to make sure you learn it. Okay, so I know it was the first unit we did, so it might not be fresh in your mind, but you got to go back and you got to review it. Okay, we spend a lot of time on it. It's a big part of the class, and but everything else kind of builds on top of it. Understanding, how the molecules behave, how they interact with each other, how atoms behave, how they interact with each other, ions behave, how they interact with each other. That kind of builds on the rest of the units. So that's why we start with it, but we got to come back and review it because it is a large part of the AP exam. Okay, so just like the Unit 4 review, I went to our visible learning document, and I highlighted all of our big title VLOs, and instead of listing all the stuff on the visible learning document, I just kind of want to go through the most important things, the things that get asked the most on the AP exam, and so that we're in good shape. Okay, so remember again, it's 1-5, or sorry, 1-1 all the way to 1-6. So we got a lot to cover. So that's why this might be multiple videos. All right. So as I'm going through my notes, remember I'm following this outline. So if when you see here 1-2 number one, right? I'm talking about this on the outline. 1-2 number, or sorry, 1-2 number one is this. Okay, so that's what I'm referring to in my notes. Okay, so for 1-1, remember it's all the nomenclature. So go to your visible learning document, look at the appendices, right? Remind yourself the names of your polyatomic ions. Remind yourself the names of, how to name ionic compounds versus covalent compounds versus acids versus organic compounds, that kind of thing. If you really want to get heavy into organic, I've posted the Organic Chemistry Handbook. You don't need to know all that stuff for the AP exam. Again, these later on when we get to molecular structure, and I'll be talking more about what you need to know from organic, or like things that'll be good for you to have memorized, so you're not wasting your time on the AP exam from organic chemistry. All right. So 1-1, we start with atomic structure. Okay. So first off, just understand protons, neutrons are in the nucleus, electrons are in the cloud around the nucleus. We understand that the electrons occupy energy levels, right? Energy level 1, energy level 2, energy level 3. Don't worry about quantum numbers. They're not going to be on there, but you will have to write electron configurations and all that stuff, which we'll talk about. And so basically, like if you get something in isotope notation, be able to tell me how many protons, neutrons, and electrons there are, right? So this number is the mass number, it's protons plus neutrons. This number here is always the atomic number, it's the number of protons. So like if in this atom of calcium, I got 20 protons, atomic number 20. If I do 41 minus 20, I get number of neutrons, 21 in this case. So this is an isotope of carbon that has a mass of 41, right? And then if it's neutral, which atoms are, and I know it's neutral because I didn't write a charge right here, same number of electrons as protons, right? Okay, so here we have an ion. So all the numbers are the same, but now the charge isn't neutral anymore. Remember, 3 plus means 3 less electrons. So I know I have 26 protons, so that means I have 23 electrons. And then again, 56 minus 26 will give me how many neutrons I have. Okay, here I got a negative ion, so that means more electrons than protons. So I have 16 protons. That means I have 18 electrons because it was minus 2. And then again, 33 minus 16 would give me how many neutrons I have. Okay. Calculating average atomic mass, right? So like, why is the atomic mass of carbon 12.01111 and not, 13? Well, there's 3 isotopes of carbon, carbon 12, carbon 13, carbon 14. But the most abundant one by far is carbon 12, and that's why the average atomic mass, which is a weighted average of the mass of each isotope weighted by their percent abundance, the majority of carbon atoms are going to be carbon 12 atoms, and a very small fraction of them are going to be carbon 13 or carbon 14. Okay, so how do we calculate average atomic mass? You just take the sum of the mass number of each isotope multiplied by its percent abundance, and you just add them all up. So, this could happen 5 times if you have 5 isotopes. It could only be like 2 times if you have 2 isotopes. But all the percentages should add up to 100. And then remember, if you're going to do it this way, if you're going to keep the percentages as a percent, then after you add everything up here, you got to divide by 100. Or, like if you have, if this percentage is 75%, and you don't want to multiply by or divide by 100 at the end, then when you plug it in to this equation to solve for average atomic mass, you would plug in 0.75, not 75%, but 0.75. Okay, and then just understanding it's not always the case, because you could have, especially the heavier elements, you could have a lot of different isotopes, and they could have a lot of their masses could vary. It might not just be, increased by a mass of one. You could have, an element that has a mass number of 45 and also a mass number of 50, and it has 5 more neutrons or something. So, but normally, you can, if you had to guess what element's the most abundant, all you have to do is go to your periodic table, especially for the lighter elements, and round to the nearest whole number. And most likely that's going to be your most abundant element. So like if you went to aluminum, 26.98 on your periodic table, right? So if we go to aluminum, 26.98. So odds are, I don't know off the top of my head, maybe, but odds are the most abundant isotope of aluminum is 27, The most abundant isotope of carbon is carbon 12. The most abundant isotope of oxygen is 16, right? So that kind of thing. Okay, now where does this data come from? It comes from something called mass spec, right? And here's an example of a mass spec readout. So here you have relative abundance, okay? And so notice whatever element this is, its most abundant isotope has a mass number of 33. So if you have abundance here, percent abundance, relative abundance, and you have mass number of isotope here, that's a mass spec readout, okay? So I think I have it up here. Here's an example, percent abundance, mass of isotope. Here's kind of another example, relative intensity in this case, but again, mass of isotope here. So mass spec just tells you the different masses of the isotopes and their percent abundance, essentially. And so here I know that, the isotope 33 is the highest percentage abundance, 34 is the lowest. But the average atomic mass is going to be a weighted average of these mass numbers weighted by their percentages, okay? All right, so also remember in Unit 1, that's when we, redid the flame test from Chemistry 1. Understand what's happening in the flame test is the electrons are jumping up to a higher energy level when you put them in the flame, and then when they fall back down, they have to release energy. They release it in the form of a photon, and if that photon has energy or wavelength or frequency, however you want to measure it, in the visible spectrum, then you see it and you go, oh, it's green or something, okay? So remember, these equations are given to you on your formula sheet. So, here I'll show you here. Let me rotate this. Rotate. And rotate one more. And rotate yet again. So let's find those. Okay, so again, you get E equals h nu. So this is energy of a photon, of a single photon, equals Planck's constant, which is given to you here. So that's h. So you don't have to memorize it. Okay, and then this symbol is frequency, which is 1 over seconds or cycles per second. You can call them hertz, but it's 1 over seconds, okay? And then this is frequency, this is also frequency. So this equation, and this equation can marry up to each other because if I use this equation and I solve for frequency, then I can come back in and plug it into this equation and use and solve for E. All right. So remember, h and c are constants. H is Planck's constant. C is the speed of light, which again is given to you here, meters per second. Okay. Remember, if you had nanometers, change this exponent to 17. Okay. And then, I don't have it in this unit review, maybe unit 2, but remember Avogadro's number, not 6.02, but use 6.022. It's on your formula sheet, but to recognize, okay, or to remember that. All right. So, when you're using these light equations, it's just make sure you're paying attention to units. Whoops, wrong thing, right? So, if I'm using this speed of light, my wavelength has to be in meters. If I'm using this Planck's constant, my energy has to be in joules. And remember, it's joules for a single photon, right? Energy of a single photon. So if you're given energy of a mole of photons, make sure you divide by Avogadro's number before you plug the E into here, because you want energy for a single photon to plug into this equation. Okay, so just watch out for that. And if you're given energy in kilojoules per mole, you'd have to divide by Avogadro's number, but then you'd also have to multiply by 1,000 to make it joules. Before you plug it in here, it's got to be joules again because you're using that Planck's constant. And then if you're solving for frequency, remember the units are just 1/seconds or seconds to the -1. Usually the way we say it is it's how many cycles of the wave pass by in a given second. That's what frequency is. How frequent is the wave? And again, sometimes it's just called hertz. All right. So if you get kilohertz, you got to multiply by 1,000 to get just hertz or 1/seconds. Okay. All right. So being able to write the electron configuration. So just remember, if you're using your periodic table, we'll come back up to here. I'll rotate. All right. Remember, there should be no problem. Like if I'm going electron configuration for iron, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. But remember, once you get here, you go 1 minus the row you're in. So 3d, not 4d, 3d, and it would be 6 for iron, right? Okay. And remember, if they don't say, if they tell you to write the full electron configuration, you have to write the full one, just like this. But if they say shorthand, remember, we could replace all of this with brackets argon, right? So shorthand notation is the noble gas notation. So you could put argon in brackets and replace all that, and then you would just finish up the electron configuration from that point. So here I have the shorthand orbital diagram. Okay, so remember, orbital diagrams, boxes are the orbitals, arrows are the electrons. All the different rules. You got the Pauli exclusion principle. In order to be in the same orbital, electrons have to have opposite spin. And then notice we went up, 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 down. That's Hud's rule, right? So when you're putting in electrons in a sublevel that has multiple orbitals, you're going to put in electrons in different orbitals first. So you don't pair up electrons until you have to. So put electrons in different orbitals first, but with the same spin. So make sure it's all ups or all downs first, and then you can start coming back and doing and start pairing them up, okay, with the opposite spin. All right. So for ions, and remember, you're either adding electrons or taking away electrons. If it's a positive ion, you're taking away that many electrons. You want to take away the valence electrons first. So that's usually the s and p electrons first. If you're removing electrons, remove it from the highest energy s and p orbitals first, not d. Okay? So a lot of times, students look at this, like, so here is neutral iron. 2 plus means take away 2 electrons. Don't take away 2 electrons from here. You take away these 2 electrons first because they're in a higher energy level 4 versus energy level 3. So take away those electrons first, then you could start taking away the 3d electrons. Okay, so iron 2 plus is going to be the same electron configuration as neutral iron, but you're going to get rid of this part of it because you lost those electrons. So 3p6, 3d6, the 4s2 electrons are what get lost first. But then iron 3 plus, that's when you have to take a third electron away. Now you can take an electron away from there, and instead of 3d6, be 3d5. Okay, but make sure you lose the s electrons first, then d electrons when you're talking about transition metals. All right. All right, so remember we have this definition of paramagnetic and diamagnetic. You might be asked this question, maybe not, who knows? It comes up once in a blue moon on the AP exam. Remember, paramagnetic means it will be affected by a magnetic field. So they might not come right out and say, is this element paramagnetic? They might say, would this atom or would this element, would atoms of this element be affected by an electric field? Or a magnetic field. If it's paramagnetic, it will be affected by a magnetic field or electric field. If it's diamagnetic, it won't. So how do you know? Well, paramagnetic means you have at least one unpaired electron. So if you go to iron, iron has 4 unpaired electrons. So it's very paramagnetic. Remember, and we we talked about this way back in Unit 1. Iron we actually call ferromagnetic because when you get four or more unpaired electrons, you're classified as ferromagnetic, which means like very paramagnetic. But I've never seen ferromagnetic show up on the AP exam. So it's just para or dia. So if you have at least one unpaired electron, you're paramagnetic. And if you have all your electrons paired up, you're diamagnetic. Okay, so if you have any unbalance in electron spin, right? That means like if you have an unpaired electron, that means you're either going to have if you just have one unpaired electron in an orbital, you're going to have at least one more up arrow than you have down arrow, right? One more up spin electron versus down spin electron. Or I guess you could, if you want to put the down arrows first, you could have one more down spin electron than up spin, right? And the more unbalanced in spin, the more affected you are going to be by a magnetic field. And like ferromagnetic means you produce your own magnetic field, right? That's why iron is magnetic. But anyway, so a quick way to know is if you're talking about elements, if it's an element at the end of a block. So, right, these are the alkaline earth metals are at the end of the S block, right? Zinc's group is at the end of the D block. The noble gases are at the end of the P block. Elements at the end of a block are diamagnetic. They'll all be paired, okay? But elements not at the end of the block are all going to be paramagnetic. So like all these elements would be paramagnetic. These elements are going to be diamagnetic. All these elements here in the P block are going to be paramagnetic, but not the noble gases, which are diamagnetic. All right, so just little things like that, might help you, answer a question more quickly on the AP exam, right? Okay. All right. So PES diagrams, remember, if you have a full PES diagram, what goes on the y-axis is the number of electrons. Okay, so relative intensity tells you the number of electrons that have that binding energy. You have binding energy, which is kind of similar to ionization energy. I've never seen it on the AP exam where it went low to high. It's always high to low. So that means, right, these electrons are most bound to the atom, and these electrons over here are the least bound electrons. And so most bound means closer to the nucleus, because again, Coulomb's law, the closer the electron is to the positive nucleus, the stronger attraction it has. So the more bound it is to the atom. So this is going to be your lower energy level electrons because they're closer to the nucleus, and these are going to be your valence electrons, your higher energy level electrons, because you're further away from the nucleus. So remember, if you're given a full PES spectrum, start labeling your peaks, right? And it's just normal electron configuration. So here's 1s2, here's 2s2, here's 2p6, here's 3s2, and then 3p1. How do I know it's 3p1? Well, it's half the peak of the 3s2. Now, how did I know this was 1s2? How do I know it's not 1s1? Well, remember, you don't get any electrons in the 2s sublevel unless this is full, right? So this is full, so 1s2. And so this is 2s2. Now, I didn't have any numbers here, so how do I know this is 2p6 and not 2p5? Well, you wouldn't get this peak if this were just 2p5. So because we have a 3s2 peak, we know that this has to be a full 2p peak, which means 2p6. All right. So if you're given a full PES, you could just label, and now you have your electron configuration. So you can go to your periodic table and say, well, what ends in 3p1? Go to your periodic table. 3p1 is aluminum. So we've identified the element. All right. So if you have a full PES, you can identify the element. Pay attention to the units of the binding energy. I've seen some AP exams where the binding energy is joules for a single electron. And so it's going to be a really small number. But if they ask you for, if they give you, if they give you, let's say they give you the energy for this, to remove this electron here, the binding energy for this electron, and they ask for the wavelength or the frequency of a photon that would be able to remove this electron, all you would have to do is, as long as this was energy in joules for a single electron. So if this was joules per mole of electrons, you would divide by Avogadro's number. If it was kilojoules per mole of electrons, then make sure you divide by Avogadro's number and multiply by 1,000. But then you would plug it into your energy equation for light, right? You plug that in here, solve for the frequency, and then if you solve for the frequency, you could solve for the wavelength. Okay, so I've seen a question like that before, right? Now you also have PES where they give you they don't give you a full spectrum, but they give you peaks for different elements. And basically you have to know which element would have the higher binding energy. So notice this is saying these are the 2s peaks for potassium and sodium. So these aren't valence electron peaks for neither potassium or sodium, right? Sodium's valence electron is 3s1, not 2s2. And potassium's valence electron is 4s1, not 2s2. So why does potassium have a higher binding energy for 2s? Well, it's because potassium has a greater nuclear charge, right? It has more protons in the nucleus. So its 2s electrons are going to be more bound to potassium's nucleus than sodium's, right? So watch out, right? We did this worksheet in class, right? Here are full spectrum, so you can figure out, right? So here 1s2, 2s2, 2p, 3. But here, this is the 2s peak for, lithium. This is the 2s peak for beryllium. So why is the 2s peak for lithium not as high as beryllium? Well, because lithium's 2s peak is 2s1, where beryllium's 2s2. Okay, but why does lithium's 2s electron have a lower binding energy than beryllium? Well, beryllium has one more proton in the nucleus, so these electrons are going to be more attracted to the nucleus, right? So those types of questions will come up. You'll get at least one PES question. Probably you might get one, and if you don't get a PES question on the multiple choice, it's definitely going to show up on the free response. It's usually going to show up at the end because they're pretty easy questions if you understand how to read PES diagrams. All right. So we're going to call that part 1 of this, unit 1 review. So I'll come back in another video to to keep going with it. All right.